Hi student, today I will show you how to design an heat exchangers. If you have a look in the left handout, I will show you the handout. Okay, we have in the handout I show you one way to find the to design heat exchangers. Okay, is using the mean temperature difference. Okay, delta T and the overall heat transfer coefficient used. Right, this one you study in week 8 already. Okay, week 8, and the purpose of this process is you have to find the length of the heat exchanger. Okay, following this step you can finish it. But today I will show you one more way to find the heat exchange to design the heat exchanger is based on what you study in week 5 and week 6. Okay, and this one is week 5. Okay, it heat conduction in the cylinder. You see this one is the cylinder, and this one is TN1, TN2. So in the our experiment, TN1 will be is a hot temperature and TN2 is a cold temperatures. Okay, so is this one will be is inner tube. Okay, so based on the equation here, you have Q equal to TN1 minus TN2 divided by the R total is thermal resistance. Okay, and total resistance, you have the equation. Okay, so you see, but in this equation, you have L is the length. You have L is the length of the pipe. Okay, so you can see based on this one, you can find the length if you know the heat transfer Q. You know TN1, TN2, and S1, S2. Okay, so we will base on this one to find the length of the heat exchanger, right? So now we will start. Okay. Okay, let me see. We'll start it. Okay, I will use one data from the experiment data. Okay, for example, after an industrial process, you have hot water at the temperature TSI is 59.3 Celsius. Okay, and you want to reduce its temperature to TSO is exists is 55.5 Celsius before coming to the seaweed system. With volumetric flow rate here is 3.9 liters per minute. Okay. And I convert this one to SI unit is meter per cube per second. Will be is 6.5 times 10 minus 5 meter cube per second. Okay. And I want to use a double pipe heat exchanger to do this one. This one is a double pipe heat exchangers. Okay. With the hot water here, this one is TSI. This one is TSO. Okay. And we use water as a cooling fluid. And because this one is T cold water in, and this one is cold water out. Okay. With the temperature in, cold water in is 18.2 Celsius, and the volumetric flow rate of cold water is 2.03 liters per minute, and convert this one to meter cube per second is 3.88 times 10 minus 5 meter cube per second. Okay, so now we have to design a double pipe heat exchanger to do this one. So before coming to design an heat exchanger, so we have to give some assumption, like the materials of the inner and outer tube, like the diameter, inside diameter and outside diameter of the inner and outer tube. Okay, so for example, for inner tube, this data, this one is exactly the same with the heat exchanger you did in the heat exchanger lab. Okay, with the inner tube is made by stainless steel. With the inside diameter here is I call this one is D1 is 10 millimeter, and outside diameter I call this one is D2 is 12 millimeter. Okay, and the outer tube, this one is made by clear acrylic. With inside diameter, I call this one D3 is 20 millimeter. Okay, outside diameter is D4 is 30 millimeter. Okay, this one is exactly the same with the heat exchanger in the heat exchanger lab. Okay, and the question here, is you have to find the length of the heat exchanger. And this one is a parallel heat exchanger. Okay, parallel heat exchanger. So based on the equation as I show you, to find the length of the heat exchanger, we have to know the total heat transfer. We have to find the average hot temperature, average cold temperature. You have to find the convection heat transfer coefficient of hot and cold water. Okay, so firstly, we find the total heat transfer of the hot water. Total heat transfer of the hot water, QS, will be equal to mass flow rate, MS, CP, delta T, T hot water in minus T hot water out. Right? So with the mass flow rate here, mass flow rate will be equal to density times volumetric flow rate. This one will be equal to density times volumetric flow rate. Okay. CP is one properties of water. So this one will be depends on the temperatures. Okay. So in this case, we will use the average temperature of the hot water. So we have to find the average temperature of hot water. With TS average, we will go to hot water in, hot water out divided by 2. And this one, the result we will have is 57.4 Celsius. Okay, so now we have to find the properties of water at 57.4. You have to find properties of water at 57.4 Celsius. Okay, so we can use appendix. Where's the appendix? Here, this one is the appendix. So properties of saturated water is table 8.15. Okay, you can go to 8.15. Okay, still loading. 8.13. 8.15. Yeah, okay. So our temperature is 57.4. So it means it will be between 55 and 60. Okay. So to find properties, you have to use interpolation between 50 and 60 Celsius. Okay, use interpolation. Okay, and the results, the properties you will have after using the interpolation, you will have some properties of water is you will have Cp here is 41H4 joule per kilogram Kelvin, and you will have viscosity here is 0.486 times 10⁻³ kilogram per meter second. You have thermal conductivity K is 0.6514 watt per meter K. You have Prandtl number a 3.1252. Okay, some properties you have. So now you apply to here. You apply to the total heat transfer of hot water equation. You will have QS is 1033.45 watt. This one is a total heat transfer of hot water. So now, if we assume as the efficiency of this one is 100%, no energy loss. Okay, so you will have heat transfer of cold water will be equal to heat transfer from the hot water. It means you have mass flow rate of cold water times Cp of cold water times temperature of cold water out minus temperature of cold water in. Okay, water in. With the mass flow rate here, is similar to hot water. We equal to density times volumetric flow rate. Okay. Or this one it will be equal to 1000 times volumetric flow rate here is 3.88. 3.88 times 10⁻⁵ is a mass flow rate. And Cp. Cp, as I said, Cp depends on the temperatures. Okay. In this case, we have cold temperature is 18.2 and hot and temperature of cold water out, we don't know. Okay. But you see, if you have a look in the properties of water at 20, around 20 here, you see, yeah, is Cp. At 20 is 4182, at 25 is 4180. Okay, it's very close. Okay, so I assume as the average temperature is 4182. Okay, so and after that I will double check. Okay, I can double check later. So I assume this one is 4182. 4182. Okay, joule per kilogram Kelvin, and I will double check this one later. Okay, when I have temperature of cold water out. Okay, temperature of cold water in here, I have 18.2 Celsius. Okay, so based on this equation, we have temperature of cold water out here is 25.5 Celsius. 25.5 Celsius. And now we will double check Cp. We will have the average temperature of cold water. Is you have Tc average will be equal to Tc in plus Tc out divided by 2, and this one equal to 21.9 Celsius. So now you can double check Cp. At 21.9 Celsius, when you use interpolation, okay, you will have Cp is roughly 4181. 4181.2. Sorry, 4181.2 joule per kilogram Kelvin. So the difference is very small. Okay, so it means this one can be accepted. So you will have the temperature of cold water out is 25.5 Celsius. Okay. And at this temperature, so it means you have the average temperatures of cold water is 21.9. Okay. 21.9 Celsius. And now we have to find, we will apply, okay, we are going to apply the equation to find the, okay, let me, wait me a little bit, I will show you the equation again. Okay, so now based on this equation, we have Q already, you have T alpha 1, T alpha 2 already. Okay, so it means we can find the R total, right? So now in the equation of R total, if you want to find L, you have to know S1 and S2 is a convection heat transfer coefficient of hot and cold water. Okay. Okay. So now we have to find it. We have hot and cold water. This one is hot water. And in the other side, I have cold water. Now we have to find S1. And how to find S? To find S, we have to know Nussen number. Okay. And how to find Nussen number? Okay, I will use this one. This one is in week 6. For turbulent flow, for example, I assume as our fluid flow is turbulent, okay, and we can double check later. So to find S, you have to find no Nussen number. And how to know Nussen number? You have to know Reynolds and Prandtl number. Prandtl number you can find from the temperature. Okay. So firstly, we have find Reynolds number. After that, Nussen number. After that is convection heat transfer coefficient. Okay. So now we start with the Reynolds number. We have the Reynolds number equal to rho V D. D here is for hot water moving inside the small pipe. Okay, so this one is D1 is inside the middle of the inner tube over mu. Rho V D over mu. Okay, with rho here you can use is 1000 kilogram per meter cube. V here is velocity. Okay, and how to get velocity? I think everyone knows velocity equal to volumetric flow rate divided by cross-section area. Volumetric flow rate of the hot water divided by cross-section area. And this one equal to volumetric flow rate of hot water is 6.5 times 10 minus 5. Divided by cross-section area is pi. The inner tube have inside diameter is 10 millimeter or 0.01 square over 4. Okay, so you have this one is 0.83 meters per second. One here is 0.01 meter inside the meter of the small tube. Viscosity we have is 0.486. 0.486 times 10 minus 3, right? So from this one, we will have Reynolds number here is, sorry. We will have the Reynolds number here is 17029. 17029. Okay, and this one is higher than 10,000. This one is fully turbulent flow. Okay, and fully turbulent flow, we can use the equation. This one, okay, Nussen number equal to this one. Reynolds number higher than 10,000 and Prandtl number is from 0.7 to 160. Our Prandtl number is 3.12. Okay, so you can use the equation. Or you can use whatever equation in the in that lecture slide. Okay. So for example, I use Knudsen number equal to 0.023 times Reynolds number power 0.8 times Prandtl number 0.3. Okay, so you have this one with the Reynolds number here is 17229 and Prandtl number, you got it here, 3.1252. 3.1252. Okay, so you will have the Knudsen number here is 78.55, right? So now is the heat convection heat transfer coefficient of hot water S1 equal to Knudsen number times K divided by diameter. Okay, with the Knudsen number, got it here. K thermal conductivity of water, hot water is 0.6514. 0.6514. The diameter here is 0.01. Okay, so you will have S1 is 5116.74. Yeah, watt per meter square Kelvin. It's hot water. So similar for cold water. Okay, cold water, you have Reynolds number go to rho V D2 D. So it's not D2 D over mu. But D in this case is a hydraulic diameter because you see you have the cold water will be moved in this area. And this area is not a super pipe. Okay, so the D here is a hydraulic diameter. And how to get the hydraulic diameter? ds here. So you have ds will go to 4 cross-section area divided by perimeter. Okay, 4 divided by 5. So this one will be is 4 times. This one is D2 and this one is D3. Okay, pi D3 square over 4 minus pi D2 square over 4 divided by the perimeter is this one plus this one. So you have pi D3 plus pi D2. Okay, so that's why ds you here you have D3 minus D2 or equal to D3 is 20 millimeter, D2 is 12 millimeter, so this one is 0.008 meter. Okay, so velocity equal to volumetric flow rate cold water divided by cross-section area. Okay, with the volumetric flow rate, yeah, is given is 3.88 times 10 minus 5, 3.88 times 10 minus 5, and cross-section area is pi d3 square over 4 minus pi d2 square over 4. Yeah, this one. Okay, so you will have velocity here is 0.168 meters per second. Okay, so based on this one, you can find Reynolds number. And when you have Reynolds number, you can find Knudsen number. Knudsen number, you find S2. It's similar to S1. Okay, so we can try to do it by the cell. I will give the result 1006 watt per meter square Kelvin. Okay, so now is the last step. You have to find the length of the heat exchanger. The length of the heat exchangers. Okay, you can base on this one, the equation. Okay, we will base on the equation in week 5. Yeah, this one. R total equal to this one and R total equal to this one. Okay. We have R total equal to T hot water average minus T cold water average divided by Q. And this one equal to 1 divided by 2 pi R1L D1 is for hot water plus log Nepal R2 divided by R1 divided by 2 pi L. Okay, this one for conduction at the inner tube plus 1 divided by 2 pi R2 L D2. This one is the equation. Sorry, not D2, it's 8. Sorry, S1 and S2, not D. Oh, sorry. Okay. So you see S1, S2 you have, right? R1, R2 you have. TS average, T co average you have. Q we have. R1 here. R1 here. K. K is thermal conductivities of the material is made used to make the inner tube. Okay, and the materials in this case is stainless steel. Okay, so we have to use a stainless steel material. So which one is you can see property of solid matter is 8.24. 8.24. 8.24 here. We have stainless steel. Okay, so you can use 15.1 watt per meter K. Okay, so you will have 14.1. That's problem. Sorry, what's the problem with this one? Okay, let me see. Is you have 15.1 is K here, this one. 15.1 watt per meter K. This one is oh sorry, still not working. Okay, 15.1 watt per meter K for thermal conductivity of the materials. Okay, so based on this one, you see just only L is one known. So you will have L here is 0.52 meter or 520 millimeter. Okay, you have 520 millimeter, right? So after this step, you have to design it using you can use SolidWorks, okay, or you can use SolidWorks, or you can use AutoCAD or whatever, okay, whatever. And the next step is modeling. Modeling, you can use SolidWorks, you can use ANSYS Fluent, okay. So actually, in YouTube, okay, you can find so many video tutorials about the ANSYS, about the SolidWorks. Okay, if you don't know how to do it, you can contact the supervisor or study coordinator. Okay. Thank you, and hope that you will have good results in the project. Thank you.